So we've reviewed power series and we've talked about how important power series are to solving differential equations, in particular those with non-constant coefficients. And here we'll get to that task of solving linear equations in particular with, non-constant coefficients through the use of power series. Okay, we're going to focus on ordinary points here, and we'll define that in a second. And of course, we're dealing with linear equations. So consider the homogeneous linear second order differential equation. I'll have something to say about non-homogeneous equations towards the end, but for now we just focus on this. So consider this homogeneous linear second order differential equation that you see here, and we give it the label asterisk, as we'll be citing it. So we're going to take this and put it in standard form by dividing by a2. So we get that double asterisk, where p of x is equal to a1 over a2, and similarly for q of x. So now the definition of what this means, ordinary points. A point x is equal to x naught is said to be an ordinary point of the differential equation asterisk if both coefficients p of x and q of x in standard form double asterisk are analytic at x naught. So we know what analytic means. It means that you could express these as power series at x naught. Okay, so an ordinary point is one where, and this is crucial, after putting it in standard form, okay, you have to be in standard form for this definition, p of x can be expressed as a power series at x naught, and q of x can be expressed as a power series at x naught. That would make x naught an ordinary point. Okay, a point that is not, an analytic, by the way, what is that? It's not just, you express it as a power series at x naught with a strictly positive radius of convergence, so not one where r equals 0. So you need some open interval around x naught such that p of x and q of x can be expressed as a power series in that open interval. A point that is not an ordinary point of this differential equation, such that p of x and q of x cannot be expressed as a power series at that point in an open interval around that point, is said to be a singular point of the differential equation. Okay, so ordinary versus singular. So some examples: all homogeneous linear second order differential equations with constant coefficients, okay, have every finite point in R being an ordinary point. And we say finite because some people include this like infinity as a point. We're not doing that. So every point is a ordinary point. Every point on the real line is an ordinary point of this. Why? Because if you divide by a here, where a is non-zero, okay? If you divide by a, you get that p is b over a and c is in q is c over a, and those are definitely analytic, right? Their power series is just equal to the first term in the power series, constant. All the other terms are 0, and so that's that. Every finite value of x in R is an ordinary point for this differential equation as well. Okay, this is already in standard form. E of x is analytic along the entire real line, okay? And sine of x is also analytic. So we've seen their Maclaurin series and that their interval of convergence is the entire real line. And so these are analytic for all x and R, and so all points are ordinary for that. X equals 0 is a singular point of this differential equation. It's already in standard form. So Why is x equals 0 a singular point? It's not because of this. It's actually because of the natural log. Okay, natural log is discontinuous at x equals 0 and hence cannot be expressed as a power series around there. Okay, at x equals 0 because it's discontinuous, and so this is discontinuous at x equals 0 and hence not analytic at x equals 0. So here q of x fails even though p of x does not. Okay, so all you need is one of those to fail, p of x or q of x or both. Okay, x equals 0 is a singular point of this. Now why is that? Well, each of these terms, like 1, x, and x, are analytic terms, but this is not in standard form. You got to put it in standard form, okay? That's very important. So once you put it in standard form, you get this. And now p of x, so there's no problem with that 1. That's analytic. Q of x is analytic. But this is discontinuous. P of x is discontinuous at x equals 0 and hence not analytic at x equals 0. So we're going to be, spending a lot of time talking about polynomial coefficients. So let's say something about those. Polynomial functions with finite powers, of course. So I'm just saying with finite power because power series are not polynomial functions. Okay, they're kind of like an infinite polynomial. We're not talking about that. But a polynomial function, so one of just degree, power n, degree n, are analytic for all points in R. Okay, so polynomial functions are analytic. Rational functions are analytic except at points where their denominator is 0. Okay, so the only problem you'll get with a rational function, what is a rational function? One where you have the ratio of two polynomials. You only run into problems where you get a discontinuity where the denominator is equal to 0. Okay, and here we're assuming the rational function is in the reduced form so that there's no common factors between the numerator and denominator. So when the denominator equals 0, that's where you have a problem. And you'll get a discontinuity and hence a function is not going to be analytic at a discontinuous point. A corollary to this theorem is that for A2, A1, and A0, in asterisk there, so this will, all points will be ordinary, okay, unless A2 equals 0 somewhere. Why? Because, well, you divide by A2. Okay, so when all of these are polynomials, okay, so assuming all of these are polynomials, the only singular points, x0, are those where A2 will equal 0. And that's obvious why, because we just finished saying that rational functions are analytic except where their denominator is 0, and if the denominator is 0 in this, you're going to get that P or Q are not analytic at those points, and hence you'll get singular points. And so that's just the special case of dealing with polynomial coefficients. And I highlight this as a theorem because, well, we're going to start looking at differential equations rather than putting them in standard form all the time. We'll just say, oh, okay, well, all of these are polynomials, and we'll just solve for where A2 equals 0, and then we'll know that those are where the singular points are, okay? Rather than going through, finding P and Q and then, just taking up time. So the only singular points are those where A2 equals 0 because you're dividing by it to put it in standard form. So x is equal to a plus or minus 1 are the only singular points of this, because these are where A2 will equal 0. And again, just for demonstrative purposes, we have to put this in standard form. And so when you do that, you'll get y plus 2x over x squared minus 1. Okay, that's P of x. And this is q of x, okay? And you could now see clearly that at x is equal to plus or minus 1, these p and q they're both, even though all we need is one of them, but they're both going to be not analytic, okay? So, all right, and what about this one? Well, where does this equal 0? It equals 0 at plus or minus I. So plus or minus I are the singular points of this differential equation. They're complex, right? This is the imaginary number. That's all right. So we still include imaginary numbers as part of singular points, and actually it's important, as we'll see with this next theorem. So if x is equal to x naught is an ordinary point of the differential equation asterisk that we have above, we can always find two linearly independent solutions in the form of a power series centered at x naught. Okay? A power series solution converges at least on some interval defined by this relation, so within this r there, where r is the distance from x naught to the closest singular point. Okay? That's the minimum radius of convergence. You can get a larger one, but this theorem guarantees at least that if you look at the distance between the ordinary point that you're going to do your expansion from, you know, have it be the center of your power series, to the closest singular point in the complex plane, then that distance, you're guaranteed that within that distance you have two linearly independent solutions of this form. Okay, so that's an important existence theorem. A solution, such as we see here, is said to be a solution about the ordinary point x naught. Remark, R in the theorem is the minimum radius of convergence. That just, you could have, this theorem guarantees that radius of convergence. That doesn't mean that you can't find a larger radius of convergence along the real line, okay? Also something to recall here, the distance in the complex plane between this point and that point is equal to this, okay? So we need that because we're going to be looking at distances of a point on the real line to the singular point. So here we found like singular point that was imaginary. So these are distances in the complex plane, okay? So let's see that theorem in action. Find the minimum radius of convergence of a power series solution to the second order differential equation that you see here about these two ordinary points. So the first one is x equals 0. And by the way, we're going to be focusing on ordinary point x equals 0. Okay? So this is very important. A2 is 0 whenever x is equal to 1 plus or minus 2i. Okay? So you get complex conjugate roots to A2. And we know that when A2 equals 0, we're going to get a singular point there. So here goes our singular points. And the ordinary, x equals 0 is then an ordinary point, okay? And now what's the distance between 0 and I plus or minus 2i? 1 plus or minus 2i. We just use this formula here, where 0 is just, if you want to write it in terms of complex numbers, this. And you just apply this formula, and you get this, okay? Now what about the ordinary point x equals negative 1? Well, x equals negative 1 expressed in complex number is this, and you apply this formula again to get square root of 8 for the radius of convergence. So here when I write plus or minus. Okay, the reason why is that the distance is the same, and let's take a quick look why, okay? So where are our singular points? It's at, and here's the real, here's the imaginary, here's 1, and here is 2, and here is minus 2, okay? Then our singular points are at 1 plus 2i, so this is 1 plus 2i, and this is 1 minus 2i, okay? Now anywhere, any point on the real line, okay, like even this point, is going to have an equal distance between those two. In particular, x equals 0, you're going to get that distance and that distance. These are going to be the same, okay? If you look at the point x equals minus 1, okay, also the same distance. So really doesn't matter, you just choose one of them. And anyway, you'll square, and that negative would just fall out anyway. And this works when you're on the real line. Okay, if we were in a complex plane, that wouldn't work, of course. So that's what I mean by this. And we will focus on solutions about ordinary point x not equals 0. For points x not equals 0, we can always change variables. Like if we did want to do a problem with ordinary point, say like minus 1 there, what we could do is define this new variable t is equal to x plus 1, right, or x minus negative 1, and basically shift. So this, we'll set that equal to t, and now we're looking at the ordinary point where t equals 0. Okay, so you could shift the problem, and because you could shift the problem, we're just going to focus on the case of the ordinary point equal to 0, okay?